Okay, in this unit we're also going to talk about intermolecular forces. This is a little bit of chapter 11, and the reason why we include it here is because the type of polarity affects properties, because it affects the intermolecular forces that exist between molecules. So we know there are 3 different states of matter: gas, liquid, and solid. They're characterized by the arrangement of the particles. Most solids are crystalline, nice neat arrangement of particles. Particles still pretty close together in a liquid, but those attractions are not as great, and they can slip and slide around each other. And as far as gases go, of course, particles are much further apart. They move more randomly. Okay. So let's talk about why this is important. So whether or not something is a solid, liquid, or gas at any given moment depends on 2 opposing things. One of those is how much energy the particles have. The more energy they have, the more they can have energy to separate, but it also depends on the strength of the attraction between them. So energy allows these attractions between these particles to break, causing the phase change. Okay, so the more energy, the more likely the phase change is going to occur, but that phase change occurring depends on the strength of the particles' interaction between each other. So we call these forces between 2 molecules intermolecular forces, as opposed to this is an intra. The intramolecular force is the force of the bond, right? Hydrogen chloride bond. But these 2 hydrogen chlorides have an intermolecular force. Okay. In the intermolecular force, the attraction between 2 hydrogen chloride molecules is very weak compared to this bond, the bond that holds the molecule together. But they are strong enough to control some physical properties, and we'll talk about those. So any intermolecular force is known as a group as van der Waals forces, named after a scientist named van der Waal, right? Van der Waal forces are any intermolecular force. There are 3 types of van der Waal forces: dipole-dipole interactions, hydrogen bonding, and London dispersion forces. There's also a 4th type, which is called ion dipole, and it's important in solutions of ions. So if I have a sodium chloride solution, the water molecule, which is polar, has an interaction with the ions. Okay, but most of the time we're not talking about this ion dipole. We're talking about molecular attractions. Okay. So dipole-dipole interactions are molecules that have permanent dipoles. So if I have, let's say, HCl, right, it's got a permanent dipole, right? And if I have a bunch of these, they're going to be oriented so that the positive side of one is attracted to the negative side, more negative side of the other. Okay? So the positive end of one is attracted to the negative end of the other, and vice versa. And we often draw these lines as dotted lines, which means that they're intermolecular forces. Okay? So they're only important when the molecules are close to each other. So the greater the dipole moment in the molecule, the more polar the molecule, right? So as the dipole moment goes up, the boiling point also goes up. And that's because it's going to take more energy to break this attraction to allow this to go off as a gas, right? Now there's a correlation that says, if you look at this table, you also see that actually, let me talk about molecular weight in a bit. Alright, London dispersion forces are a specific type of van der Waals force. So here we have helium, which we don't consider to be a polar atom, right? No atoms by themselves are polar, but even if I think about just a helium atom, it's got 2 electrons, right? And even though we generally would probably think about the electrons being on opposite sides of the nucleus, in fact, it's possible for any split second that the electrons are closer to each other than they are, and they're not equally spaced apart. And what that does is it sets up a temporary dipole. But as quickly as it forms, it also comes apart, right? Because the electrons are always moving. So it's an instantaneous, very weak intermolecular force. So for that one instance, the atom or the molecule can become polar. And if I have another helium beside it that also has dipole forces, it can, or even if it doesn't have the London dispersion force, it can cause the other molecule or another atom to polarize. It can cause the electrons to shift, right, and cause the other one to polarize. So one becomes slightly polar with this skewing of electrons, can cause an adjacent one to also become skewed. So we have these instantaneous dipole, and we call it an induced dipole. So you get a dipole in one, it induces a dipole in an adjacent one. So these forces are present in all molecules. Doesn't matter whether they are polar or nonpolar. So if you ask what kind of van der Waals forces exist in nonpolar molecules, the only thing that they would have is London dispersion forces. Okay, they're not polar. Okay. So we call the tendency of an electron cloud to distort in this way polarizability. So can I polarize a molecule by causing the electrons to skew? So the things that affect London dispersion forces are the shape of the molecule, right? So here I have basically the same formula, and here this pentane is more linear. Here it's more circular, and because this has more surface area and more electrons on the surface, it tends to have slightly greater London dispersion forces. Now the other thing that you will often see, and I almost referred to this earlier, is the molecular weight. So I have all halogens, right? And as the molecular weight increase, we also see an increase in boiling point. So what's important here, though, is it's not the molecular weight that causes the increase in boiling point, it's the number of electrons. So as I go down this row, I'm adding a whole nother shell of electrons, right? So it's the increase in the number of electrons. The more electrons I have, the more they can skew. So on the AP exam, if there's a question about what causes a higher boiling point, you can't say iodine has a higher boiling point than chlorine because it's got a higher molecular weight. You have to say it's because it has more electrons. Okay, so it's all about larger electron clouds, which are easier to polarize. So which is going to have a greater effect, a dipole-dipole or a dispersion force? So if two molecules are about the same size and shape, dipole-dipoles will be stronger. But if you have a really large molecule and another that's small, then you might have dispersion forces that dominate and dictate the physical properties. But usually the dipoles are going to be greater than the dispersion forces. Okay, so here we have, let's just focus on the blue line first. Here we have increase in molecular weight. We have, in the all cases, we have a tetrahedron shape. We have carbon and then silicon. So in all cases, this is the same group in the periodic table: carbon, silicon, germanium, and tin. And as I increase molecular weight, I'm also increasing electrons, and I have a predictable increase in the temperature at boiling. If I look at this similar kind of thing going on, though, with the adjacent group where I have oxygen, sulfur, selenium, and tellurium, it's a different picture, and this water is acting like a big anomaly. So what's going on with water? Okay, in this case we have a special case of van der Waals forces or intermolecular forces called hydrogen bonding. And the dipole-dipole interaction, when hydrogen is bonded to one of these, nitrogen, oxygen, or fluorine, it's unusually strong. And the way you remember which atoms are involved, or hydrogen bonding is possible, just remember ET, right? And it's phone, home, right? Phone, home. Okay. So it's unusually strong when the hydrogen is attached to a nitrogen, oxygen, or fluorine. And we call these interactions hydrogen bonding. And it arises in large part because the nitrogen, oxygen, and fluorine are all very, very electronegative. Really have a large pull on the atom, causing greater dipoles. There's also a little bit of this is that when you have one of these attracted to a hydrogen, the nucleus of the hydrogen is somewhat exposed, making it even more polar. Okay? So here's a chart that you can refer to when you're thinking about intermolecular forces. So the important thing here is that intermolecular forces affect a lot of physical properties. And it's all about the strength of attraction between these particles that determines things like boiling point. Right. So one property that's affected by intermolecular forces is viscosity. So resistance of flow of a liquid to flow is called its viscosity. So the faster it flows, something like milk flowing, is a lot less viscous than something like pancake syrup, very high viscosity. And it's related to how easily the particles can slip and slide past each other. Okay, so the greater the intermolecular forces, okay, the greater the viscosity, because those particles get hung up on each other if there's intermolecular forces. It's also related to temperature. So if you think about pancake syrup when it's cold versus pancake syrup when it's warm, once you warm it up, it will actually become much less viscous and pour more easily. Surface tension is another property, and something you can see a lot of in water, that is related to intermolecular forces. And what you actually have here on the surface of this water is you have all of these waters attracted to each other through hydrogen bonding, and they form a sort of skin. They're very, very strong, and if you put like water on a penny, right, keep putting drops down, that water just mounds and mounds and mounds. And that's because these attractions between those water molecules is very strong, which is what allows this little dragonfly to actually stay on top of the water. Causes high surface tension. That's what surface tension is. Okay, so if we think about phase changes going from a solid to a liquid and a liquid to a gas, and how much energy it takes, the energy it takes for these changes to occur depends on the intermolecular forces, right? How tightly is this solid, are the solid particles attracted to each other? How strongly are the liquid particles attracted to each other? And that impacts how much energy it takes to break those attractions, directly related to intermolecular forces. Okay, so the heat of fusion is directly related to the melting point, right? So so if you think about heat of vaporization, this is the temperature at which something boils, right? It's going to take more energy for larger molecules, or molecules with higher intermolecular forces, to vaporize. Okay? So heat of vaporization is the energy required to change a liquid at its boiling point to a gas, right? So the heat added to a system at the melting point and boiling point is pulling apart, so the energy in here is pulling apart the attractions, right? Okay, it takes more energy to do that. So that the temperature of a substance doesn't change during a phase change. Another property that's similar to boiling point is vapor pressure. So if I have a liquid, let's say, and I have a water bottle, and I have water in here, there's always going to be some amount of water molecules in the water vapor as a gas, right? And the higher the temperature, the more water molecules I'll have, and the more I'll see condensation in the bottle, right? So, or I'll see the droplets on the side, okay? So the higher the energy, the more particles I have that are able to escape and go into the vapor phase, okay? So the fraction of the molecules that have enough energy to escape increases as temperature increases, right? And it also is related to the intermolecular forces. Okay, so as more molecules escape, they exert more pressure until they reach some equilibrium. Okay, and these are directly related, again, to the intermolecular forces. So I'm going to have a greater vapor pressure for things that have greater attractions, okay? And they're going to be, all of them will be affected by temperature. So something's going to be, let me see. So we're going to stop there. Vapor pressure, boiling, anything that's caused by attractions of molecules is going to be affected by increasing intermolecular force. So we're going to stop there.